Welcome to the video lecture. As a part of electrical machines, today I am going to explain short circuit test on single phase transformer. These are the learning objectives to calculate the losses and predetermine efficiency at different loads at different power factors and to obtain the series equivalent circuit parameters of the single phase transformer. So, the main aim of the short circuit test is to determine copper loss of a given transformer and draw the equivalent circuit of a given transformer and plot the efficiency and regulation curves. So, this is the circuit diagram of single phase transformer. Yeah, actually in the short circuit test, generally this test is done in the HV side and LV side is short circuit, must be short circuit. Reason that actually in SC test we are not applying the rated voltage. So, very little voltage applied up to it reach the rated current by this current. So, this circuit, why? Because any winding it withstand up to the rated current. So, that we are so once as per circuit diagram you connect the circuit, just you are concentrate an ammeter and by using this auto transformer a little bit voltage is injected. So, automatically the current is increasing. So, we are observed where it is reached the rated current. So, immediately we note down the values, of the transformer. So, this is the procedure. Connect the circuit as per circuit diagram, switch on the AC supply and increase the applied voltage slowly till the load current flows through the circuit and record no load current, applied voltage and power of the how much power is consumed. So, this is the tabular form for the observe the values. We record the under rated current, we note down the current ISC and under short circuit condition at rated current how much voltage applied, that is called as VSC, and how much power is consumed, that is noted by the WSC in watts. So, this is the by using SC test data, generally we are calculating the equivalent circuit, there is series equivalent circuit parameters of the single phase transformer, that is called as winding parameter. Here the R equivalent is nothing but this is the total resistance of the total winding resistance of the transformer with respect to HV side, and Z equivalent is nothing but this is called as Z equivalent total impedance of the winding with respect to HV, and finally by using that formula we are calculating the X equivalent of the HV winding with respect to HV side. So, this is the equivalent circuit, and R equivalent dash and X equivalent dash generally are referred and HV side. So, your R equivalent dash and X equivalent dash whatever it may be, by using these formulas we calculated and provided here. So, but how, why, what happened this R naught and XM under OC test, this SC test, just I have to show this. Same similarly in the previous class I take the in place of transformer I am taking the their equivalent circuit. This is the R equivalent dash and X equivalent dash, and we are providing. So, secondary short circuited, so it must be shorted, SC short circuit. So, this is called as R naught, this is called as XM, and this is called as I naught. Here I think we are providing the wattmeter also. Oh, maybe very simple way. This is an ammeter. Here wattmeter is provided here, and here the voltage is provided VSC. So, actually this voltage applied through auto transformer, because we are not apply the full voltage, it measures the short circuit current and it gives the WSC value. So, Maybe the big transformer, maybe generally this experiment, whatever it may be, conducted we are conducted under short circuit condition, that is why we are not applied full voltage. But here across these shunt parameters, what are the voltage, that is called as the VSC, but VSC is very very less. For example, the 11 kV transformer or maybe that value, so we are apply very little voltage, we are giving the VSC maybe 1 or 2% at least 5%. So compared to I naught values, already it is very less because of the high impedance. So but also now we can apply the very low voltage, I naught value is very 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 small, so that is why it is neglected compared to their rated current. Why? Because in SC test I told already, here the I naught is very neglected in the 1000 amperes, maybe it is 1 amp, maybe it is not neglected. For simplify, for to avoid the complications, I naught is neglected. So the remaining current is going to here only. So under SC test, generally the transformer is acting like this only. So we are nullified. So what happened now? So we are the across this winding we are apply the VSC, and the what the current is passing, ISC. Here the WSC is given to the total copper losses, that means that is called as ISC square R equivalent dash, R equivalent dash. So by using this formula, we are calculating the R equivalent dash is equal to WSC by ISC square. This is the one of the formula. So what the power is the consumed in that equivalent circuit. So here this SC test, this wattmeter is the copper loss of the both windings, copper loss of the both windings. So it is you are finding the full load copper loss, and also I am finding the R equivalent their winding resistance, series equivalent resistance. Another term is only we have the X equivalent, but how to calculate? So across this impedance we are connecting the voltmeter and ammeter. VSC by ISC are getting, so total impedance of the Z equivalent dash, this is called as the Z equivalent dash. So here the Z equivalent dash is equal to VSC by ISC. So VSC by ISC. So by using this formula we calculated the total impedance of the winding, and already R equivalent dash is known. So once you know these two parameter, the another parameter X equivalent dash is equal to that equal to root of Z equivalent dash minus R equivalent dash whole square. Why? Because Z equivalent is equal to R equivalent square plus S equivalent. So here the Z equivalent is equal to R equivalent plus J of X equivalent. So X equivalent, but all are so rotation. Based on this formula we can calculate the X equivalent dash. So like this, once you calculated the but series parameters, now we are ready to calculate the voltage regulation also, So here the maybe we are giving this is the formulas to find out the percentage of voltage regulation. You know the I2 is nothing but the rated current with respect to secondary side, and we calculate R equivalent dash is known already. Based on that we are calculate R equivalent cos pi naught 2 and I2 X equivalent sin pi 2 by E2. So voltage regulation formula, it is the drop of actual voltage input voltage. So what is the actual terminal voltage and induced voltage. So and also because of that reason, due to winding parameters, some of the voltage drop is occur. So based on that we are calculating the percentage. Here plus is nothing but the general used for the lagging power factors. Suppose the load is, why? It is a predetermination technique. So we are not providing directly, we are not finding without connecting the load. Without connecting the load also we are finding the regulation. So here, so we are by OC test we are calculating the iron losses, by SC test we are calculating the copper losses, and after that by using test data we are calculating the circuit parameters and equivalent circuit parameters of transformer. Now for example cos pi naught is equal to, you assume like that, suppose the load is connected to the unity power factor, cos pi value is taken as 1 and sin pi equal to 0, and apply the values, we are getting the regulations. Like that we are calculating the different power factors. Maybe the load is connected to 0.8 lagging load and 0.6 lagging load and 0.4, 0.2 like this, we are calculating different power factor condition, how much regulation is occurred, you are identify. Like that also your minus is used for the leading power factors. You are using the leading. Suppose you are connecting the leading load, so automatically the maybe the power factor is injected. So the value, this is the formula, based on that we are calculating the percentage of regulation. So iron loss is equal to W naught, it is taking from the OC test. Copper loss is taken from the WSC, it is SC test, from SC test. And efficiency formula, actually it is the capacity of the transformer, maybe it is the maybe 1 kVA or 2 kVA or 3 kVA, 5 kVA, whatever it may be. In terms of kVAs into the 1000, it is converted to volt amperes into cos pi, the power factor type of the load, maybe unity power factor cos pi value 1. So we substitute that values, and this is the capacity, and so output by output plus losses, we are getting the efficiency of the transformer. Like that we want to conduct the offload efficiency P naught by 2 we are considering here, and also here the P naught by 2, and here the WS is nothing but it is I square R loss, that is why current is off value. So simply here the 4 times it is regular, so by we are applied here value. So based on that there are different power factors, efficiency, different load condition, what is the efficiency of the transformer, easily analyzed by this formula. Another one is the percentage of the regulation. By using this formula we are calculating the regulation curves. So in different loads with the different power factors, so we are calculating the regulation, how it is behave the transformer. So once you calculate the different by using that formulas, we plot these graphs, output power versus efficiency. So we are observed that 1/4 load and 3 off load and 3/4 load and full load. Generally in mission the 3/4 load, it gives the maximum efficiency. This is the regular curve. So lagging power factor, generally it is the positive regulation. In leading power factor, it gives the negative regulations. So thank you.